Hello and welcome to the fourth virtual Philip J. Currie Dinosaur Museum Speaker Series, where we have paleontology guests call in for a presentation on science, fossils, and dinosaurs, and where the public will be able to ask questions both here at the museum and live on YouTube. For the viewers at home, you can leave your questions in the comment section and I will read them to Rebekah at the end of the talk. First off, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis people whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, Rebekah Weiss will be presenting new insights from the Pipestone Creek Bonebed. Rebekah grew up on a farm just outside of Toronto, Ontario, where from a young age she grew fascinated with dinosaurs. She completed her undergrad in paleontology at Carleton University in Ottawa, Ontario, and then went on to pursue her master's at the University of Alberta in Edmonton, where she recently defended her master's thesis on Pachyrhinosaurus from Wembley, Alberta. She has taken part in paleontological fieldwork throughout Alberta, but most notably in the Grand Prairie area as part of the Boreal Alberta Dinosaur Project, led by her master supervisor, Dr. Corin Sullivan. Thank you, Rebekah, for joining us, and I will let you take it away.
All righty. All right, hello everyone. Thank you so much for joining us on this Saturday afternoon, I guess depending what time zone you're in. So thank you so much for the introduction. My name is Rebekah Weiss, and I just completed my master's at the University of Alberta. Now, having defended my thesis on Pachyrhinosaurus from the Pipestone Creek Bonebed, I'm just going to be telling you today a little bit about my research and kind of the two major findings from my thesis. So without further ado, let's get started. All right, so first off, a little bit of history about Pachyrhinosaurus. Now, Pachyrhinosaurus is a ceratopsian dinosaur or a horned dinosaur, so very closely related to Triceratops. Pachyrhinosaurus was first discovered in 1945 by a very famous paleontologist named Charles Sternberg. He officially named Pachyrhinosaurus as a new genus and species in 1950. At the time, it was considered to be a very unique ceratopsian, as it had this very distinct nasal boss on its frill, as its skull, as you see here. Up until this point, though, all other ceratopsians, instead of having a boss, they had a very large nasal horn instead of this boss. So because of this, Pachyrhinosaurus was thought to be so weird that there was no way that this boss could actually be a true feature of the specimen. And this led to a couple of kind of silly reconstructions if you look at them today. So you can see the theory was that this boss, instead of being a true feature, was just the basis of a very large nasal horn and led to some reconstructions with these very huge nasal horns that is it's a little bit ridiculous because this horn would be so heavy that ceratopsian skulls already have a lot of weight to them. So this extra very long horn just isn't really feasible. And as more and more Pachyrhinosaurus specimens became discovered, it became clear that this was a true, what we call a true morphological feature, a true diagnostic feature of the group. So at this point, there are 3 known species of Pachyrhinosaurus. The first one being Pachyrhinosaurus canadensis, which was the first one discovered by Charles Sternberg near the Lethbridge region of Alberta, and has since been discovered in the Drumheller region as well. From there, in 1972, the second species, Pachyrhinosaurus lakustai, was discovered in the Grand Prairie region of Alberta, which is the species I'll be discussing more in detail today. Next was Pachyrhinosaurus paratorum, which was discovered on the northern slope of Alaska in 2012. Now, it is worth noting that there is a 4th potential species of Pachyrhinosaurus that has also been discovered in the Grand Prairie region of Alberta, but it's speculated as to whether this is a new species of Pachyrhinosaurus or whether this is just another occurrence of Pachyrhinosaurus canadensis. But up until this point, we're not certain on its identity. But enough of that, let's dive into Pachyrhinosaurus lakustai specifically. So Pachyrhinosaurus lakustai is from one locality called the Pipestone Creek Bonebed, which is very close to the Philip J. Currie Dinosaur Museum in Wembley. Just to give you an idea, here's the museum and it's just kind of south of there. So for those of you viewing from the museum, if you haven't been to the bonebed at all, I highly recommend it. I know the museum offers a few walking tours or their paleontologist for a day program. It's a really incredible site. It's very unique, as I'll be discussing shortly. So I highly recommend checking it out if you get a chance. So Pipestone Creek was initially discovered in 1972 by a high school teacher at the time named Lakustai. He's often spent time in this area just collecting various fragments of fossils for his own collection. But one day he actually was walking along and discovered an entire skull eroding out of the cliff, which later we discovered to belong to this new species, Pachyrhinosaurus lakustai. Since its discovery, it has been kind of sporadically excavated over the last few decades by different groups. First off being the Royal Tyrrell Museum, who began excavation in the 1980s. Since then, the University of Alberta has also excavated the site, and currently the Philip J. Currie Museum annually runs their fieldwork there. Now, we know that Pipestone is approximately 73 million years old, and the way we know that is by looking at the different kind of layers of rock surrounding the bonebed. So for those of you who aren't familiar with this, this is something called a stratigraphic column, which is just a way of us paleontologists and geologists to represent the different rock layers in an area. So in this case, we know exactly where the bone layer resides within the different rocks around it. So in this case, we have the bone layer residing here. And thankfully, there was a volcanic ash layer discovered just above the bone layer, which actually we could use radiometric dating to determine that it was approximately 73 million years old. So that gives us an estimate of how old these bones are. So this puts them in the late Cretaceous. So this is close to the end of the extinction of the dinosaurs, but not quite at the very end of it. Pipestone Creek is often described as one of the densest dinosaur bone beds in the world. To give you an idea for that, here's a quarry map from when the Royal Tyrrell Museum was excavating there. And you can see just the immense density. All of these outlines are outlines of bones. So they're all just very closely stacked on top of each other. And in some places, there's up to 200 bones per square meter. So this is much denser than definitely any other quarry that I have worked at, and most quarries that most people have worked at. Just to give another appreciation for that, here's a photo that I took in the field a couple years ago, and you can just see how closely stacked all of these bones are. So typically when you're excavating a quarry, you will find your one element, and the idea is to trace the margin of that element. So see how far does it go? Does it go really far one way? Does it go into a cliff? Do you need to take down some of that cliff? However, with pipestone, we run into a very immense difficulty when we're trying to remove one bone from the quarry. We'll start to trace the margin of the bone, and more often than not, you will run into another bone that is actually on top of that first one. So it's basically a crazy Tetris game of trying to figure out which bone is on top, as you can only take out the very top one first and work your way down through the quarry. So it takes a long time even just to excavate a very small area in pipestone just because of this density there. Now pipestone, with all of these elements, with hundreds of elements being collected from there over the decades, we have pretty well every single skeleton, every single bone in the skeleton represented at this site. And not only that, most of these bones are also represented by what we call varying stages in ontogeny. So that refers to just various stages in age. So to give you an idea of that, here's a series of humeri. So these are your upper arm bone. And you can see just the range in size, everything from a very small baby all the way up to what we assume to be a fully grown adult, and pretty well everything in between. So this is a very unique occurrence that we don't get to see in most other bone beds. So that means that we can actually study Pachyrhinosaurus lakustai in ways that we can't study all other ceratopsians. Now, because of all these elements that have been collected, various studies have been done on this site, but of course there's still more to look at. For instance, my thesis was all focusing on what we call the postcrania of the skeleton. So this is just the part of the skeleton that doesn't include the skull. In ceratopsians, there is so much information we can gather by looking at the skull because they're always so unique. They have these really cool ornamentations and these horns. So that's what most paleontologists will study with ceratopsians, but there's still more information that we can gain by studying the postcrania of these dinosaurs. So that's kind of what my thesis was focusing on. But I'm just going to focus on kind of two different aspects of it. And the first one I kind of studied as a point of opportunity. And by that, I mean with all of the different stages in ontogeny represented at Pipestone, it gives us an opportunity to study the growth of these animals, how they change throughout their life. So to do this, I wanted to create what we call a growth curve. So to determine how the dinosaur grew, what rates it grew at different times in its life, and so on and so forth. So the first step to doing this is to determine the different age of dinosaurs, of the specific dinosaurs. So paleontologists actually have a pretty unique way of doing this that I'm going to kind of discuss in a little more detail for you guys, because I think it's a really cool analysis that we do that most people don't actually get to see. So how do we age a dinosaur? So first off, you want to select your element. So for this, I selected just a range of humeri. So remember, that's the upper arm bone. So the first step is just to make your first cut. So this is the bone that I actually sectioned. This is a humerus, but it's just more fragmentary, so it's lost kind of each end of it, making it more feasible to actually cut into pieces. Obviously, we don't typically like to cut up our prize specimens that are completely complete. And this is just to give you an idea of what this bone would have looked like. So you make the first cut, and that will give you a view of what the cross section of the bone looks like. So from there, you can see very distinctly where the marrow would have been in the bone. So it's a very distinct marrow cavity kind of surrounded by the actual bone itself. From there, this kind of puck of bone that you have cut off gets embedded in resin. So it's just kind of this clear epoxy that surrounds it that will solidify, and it will give you this very clear puck with the element just kind of nestled in there, surrounded by this clear resin. Just to note, these little labels kind of thrown in here are just to help me as a paleontologist determine what side of the bone I'm looking at. So they just refer to different anatomical directions of the bone. Just kind of to keep everything straight. Next up, you make the second cut. So to do this, we use kind of this fancy machine called an isomet, which the puck will connect to this kind of arm-like structure, and it will just slowly fall onto the blade, as you see here. And that does this based on weight. So it will just very slowly cut through that puck and gives you a very clean line, which is what we want. So you make that second cut, you have your puck with a bit of the bone cross-section revealed in it. From there, you just glue it onto your slide. And lastly, you cut it and just grind it down to the desired thickness. So the idea is to get it down to a thickness that you can actually view it through a microscope so that we're able to see these microstructures. Because these microstructures are the very important thing for determining the age of the dinosaur. And these are something called lines of arrested growth, or lags. And you can see this pretty clearly in this section, this very distinct ring in the element. And this is much like the growth rings that you see in trees. And each lag represents a different year in the animal's life. So by counting the number of lags in a specimen, we can determine how old that dinosaur was when it died. Just to give you a clearer picture of that, so these kind of pink lines represent the lags that I actually was able to view in this specimen. So this one had 3 legs able to be identified, which means that this animal was most likely 3 years old when it died. I also did this with a series of other humeri. So this is the largest one that I actually sectioned. And one thing you might notice is that the marrow cavity in this element is much larger than the smaller one that we saw before. And that is one of the key features that we see when we section older individuals. And it's a case of remodeling. And it's to the point, just to see how there are still a number of legs able to be drawn in this specimen. But the marrow cavity takes up pretty well the circumference of that smaller humerus that we looked at earlier. So it has expanded so much that we actually would assume that some of the legs were lost from earlier on in life. And like I said, this is due to something called remodeling. So there's two main things that occur in a bone for it to be remodeled, for these legs from earlier on in life to be lost. The first is that expansion of what we call the medullary cavity. So that marrow cavity will expand and eat up the legs that were laid earlier on in the animal's life. But also you get the formation of something called secondary osteons. Now osteons typically just make up bone. However, secondary osteons will form later on in life, and they actually will form on top of previously lain lag lines. So again, you can see kind of clearly the lags in the specimen, but you'll also notice the secondary osteons are forming right on the lag lines. So you can imagine as the secondary osteons get more and more dense, they eat more and more of the lag line up so that it at one point will essentially just disappear and we won't be able to, sorry, we won't be able to count it. The third thing to note in this adult specimen is something called an external fundamental system, or an EFS. And an EFS indicates that this animal is at skeletal maturity. So it's pretty well as old as it's going to get, as big as it's going to get. And what happens when an animal gets very old, it doesn't grow nearly as much every single year. It will still grow ever so slightly. So that's why every year lags are still being deposited. However, during each growth cycle, during each year, the bone doesn't grow nearly as much. So the lags are stacked very closely to each other. And these lags kind of combined, stacked very closely, form that external fundamental system. So this is how we can determine if an animal is actually skeletally mature or if it's still growing. So from here, we can actually start to create our growth curve for Pachyrhinosaurus lakustai. And how we do that is we will superimpose the lags from the younger specimens onto the older specimens and use the circumference of each specimen, use the size of each lag to determine how big that animal was at that year in its life. So to kind of show you firsthand, here's the youngest individual I sectioned. And in this case, no lags were identified. So we can determine that it was less than 1 year old when it died. So therefore, you plot it just under 1 year old. And using the circumference of the element, we can actually use an equation to determine or to estimate the body mass that that individual was at death. Next up, we look at the lag with the smallest circumference. So that was the smallest lag in this specimen here. And we can plot that against the body mass onto that same graph with that younger individual. And we keep going from there. So you move on to that third individual. And those lags actually had very similar circumferences to the lags from that second individual. So we can assume that they actually represent the same years in life that those lags were deposited in the other individual. So that's when you have a little bit of overlap. And this continues as you go into the older specimens, you actually start to see the growth kind of drastically increase. So as juveniles, they're growing relatively rapidly, but then after they reach age 4, age 5, that growth rate accelerates drastically. So think about humans in their teenage years. They grow really, really fast. And then they will reach a point around age 12 or 13 where that growth really drastically decreases. And once we plot that oldest individual on there, it follows that same trend of the growth drastically decreasing. So there we have it. We created a growth curve for Pachyrhinosaurus. So this gives us an idea of the growth rates of and how they change through the animal's life. And also from this, we can determine the age of that oldest individual. So by kind of superimposing all of these lags, we can estimate that this oldest individual was approximately 21 years old when it died. Now, if we compare this to other ceratopsians that have been studied in this way, this is actually the oldest ceratopsian individual ever found and studied in this method. So that it comes out at 21 years old. The closest would be Pachyrhinosaurus paratorum, so that's the Alaskan species of Pachyrhinosaurus, was determined to be 18 years old. From there, Centrosaurus in southern Alberta came out at 14 years old. Dinosaurus was determined to be 6 years old. Now, one Triceratops was sectioned where they actually only found 2 lag-like markers. So we would assume that this individual was only 2 years old when it died. However, this doesn't completely make sense because this specimen of Triceratops was so large that we assumed that it is an adult specimen. It didn't really make sense that it was only 2 years old. And this was also the case with Utaceratops and Chasmosaurus, where no legs were identified in these very large specimens that we would assume to be adults, but based on the legs, they are less than 1 year old. So this has actually led quite a few ceratopsian paleontologists to propose something called the latitudinal gradient hypothesis. So this is the idea that if we look at the maximum number of lags in one individual of a species, so forget the whole superimposing to determine the age, this is just looking at one individual. So in Pachyrhinosaurus, one individual had 15 legs, which was the maximum number I found in one single specimen. So if we actually start to compare those maximum number of legs in specimens, we start to see a pretty clear trend. So starting at the most southern latitudes, Utaceratops and Chasmosaurus didn't have any legs identified. Then as we continue slightly more north to Wyoming, Triceratops had 2 legs identified, so it's starting to increase ever so slightly. From there, Dinosaurus in western Montana had 5 legs identified in one specimen. Centrosaurus in southern Alberta had 7. And prior to my research, Pachyrhinosaurus paratorum in Alaska had 18 legs identified. Now, Pachyrhinosaurus lakustai actually fits in perfectly to this gradient. As I mentioned, they have 15 legs identified in one specimen. So it fits in perfectly to this idea that as latitude increases, then so does the number of legs. And this is thought to be due to an increase in seasonality. So if you imagine more northern climates, especially those of you that are viewing from Grand Prairie, I know you appreciate the very drastic cold seasons that we get. And this is something that even occurred in the Cretaceous as well, although maybe not to as great of an extent as we see today. So the more northern species will experience very harsh winters. Now, lags are thought to deposit annually in the winter because of a decrease in resources. So in the winter, there's not that many plants for animals to eat, so they can't grow nearly as much. So that's why their bone growth ceases and they reach this period of what we call non-deposition. And that is what forms those lags. So the bone just kind of stops growing and forms that ring. And once spring hits, plants start coming out, there's more resources available for them to eat, the animal is able to grow again until the next winter hits, and so on and so forth. And that's why you get all of those rings generated year after year. However, in more southern climates, there isn't nearly as much seasonality there isn't as much seasonality. So if you continue to say where Utaceratops and Chasmosaurus were, potentially they didn't experience any seasonality at all. They didn't have any of those harsh winters. So they didn't actually have any opportunity for lags to be deposited. So let's change pace a little bit now. And this is moving on to kind of the second main finding from my thesis. And this is the idea that, this is looking at the gait and step cycle of Pachyrhinosaurus. So first, a little bit of background about what I'm talking about. So gait just refers to the posture of different animals. And there's three main gaits that we see in the animal kingdom. The first one is a sprawling gait, in which the elbows are pointed pretty well horizontally. And this is kind of what we see in modern lizards today. And the second major one we see is an erect gait, where the forelimb is pretty well stacked neatly on top of itself. And we see this in animals today, such as horses and elephants. And the third main gait is a semi-erect gait, which is basically halfway between the two. Now, the gait of dinosaurs has been a debate since the dawn of paleontology. So here is actually the first reconstruction of Triceratops when it was discovered by Marsh. So this is from 1888. So this is way back in the time of the Bone Wars, as well as the first ever Triceratops mount from the Pan American Expo in 1901. Now, in both these cases, they have a pretty erect gait. So they're standing up pretty well as straight as they possibly could. But there is a major problem with them having this gait. And that is that with their limbs being so long and their head so far above the ground and their neck being pretty small itself, they probably wouldn't actually even be able to reach the ground with their head. So they wouldn't actually be able to graze. So this is improbable. So this led paleontologists to kind of change pace a little bit. And at this time, so this is moving on to 1916 and to 1926 kind of era. At this time, dinosaurs were thought to be these very dumb, these very slow moving reptiles. So this led to mounts like these Chasmosaurus mounts from the Canadian Museum of Nature in 1926, where they have that sprawling gait that we see in reptiles today. And this, again, rather ridiculous representation of Diplodocus from 1916. It seems a little bit more ridiculous with sauropods, as they just have so much mass that it's hard to fathom them actually having this gait, because they most likely would not be able to actually hold up their entire body. So again, paleontologists kind of changed their tune to change the gait once more. And this is now kind of the modern thought, especially with ceratopsians, that they had a semi-erect gait. So this is, again, halfway between sprawling and erect. It's kind of a nice middle ground. And this is what modern ceratopsian mounts look like now. But there's still different studies being done to test this hypothesis to see if all ceratopsians had the same gait, or if there was variation even within that group. One such study was done by Thompson and Holmes in 2007, where they studied this mount of Chasmosaurus from the Canadian Museum of Nature. Just to give you an idea, this is what Chasmosaurus looks like. This is one from the Royal Tyrrell Museum. And they studied the forelimb of Chasmosaurus to determine through its step cycle how exactly the forelimb would articulate. So that just means how the forelimb would fit together. And that gave them this idea here. They also tested their hypothesis with ceratopsian trackway data to determine if this would actually fit the trackways, because if their step cycle does not fit the trackways, then it most likely is not true. And just another shot kind of from the front of what their step cycle would have looked like. Now, this Chasmosaurus specimen also had another feature that is very unique. And that comes from the manus, or the hand of the specimen. I'll draw your attention to the first digit here, where the first digit is really deformed and kind of mangled. For reference, here is the first metacarpal, so this element at the top here of this specimen. And this is what a first metacarpal looks like in another ceratopsian. So you can see just how deformed, how mutated this specimen is. So there's something strange going on here. And this deformation was also observed in another Chasmosaurus mount from the Royal Ontario Museum. And Again, in the first digits of both hands this time, there was some level of deformation. Therefore, this has led a few researchers to hypothesize that this was actually due to that step cycle that Thompson and Holmes proposed. And I'll walk you through what I mean by that. So in their step cycle, it would force the humerus to rotate slightly inwards as the animal walked in what we call a propulsive phase, so as the animal walked forward. From there, this would force the radius, this element here, to again rotate inwards. This would force extra stress on the first digits of the manus. And therefore, this extra stress could be what's causing that deformation in the first digits of those Chasmosaurus specimens. This also would have been added to with that added weight of the older ceratopsians, as this deformation has only been observed in older individuals. We haven't been able to identify this same deformation in younger individuals. So it's thought that this could be due to the weight of the animal all resting on that thumb. But there's probably something else going on here. Again, as I mentioned, we haven't seen this in juveniles, so there's probably more to it. And so it's also thought that this stress is coupled with some sort of disease or infection that's brought on due to these animals' mature age. So how does this relate to Pachyrhinosaurus? So Thompson and Holmes actually proposed a few key features from the forelimbs of Pachyrhinosaurus, or of Chasmosaurus, sorry, that I was able to relate to the features I observed in Pachyrhinosaurus forelimbs. So I'll walk you through a few of those features. So the first one comes from the humerus. So this humerus here on the left is from Pachyrhinosaurus, and from the right from Chasmosaurus. And Thompson and Holmes noticed that Chasmosaurus has a very large process here called the medial tubercle, which, given a more erect gait, this animal, this medial tubercle would interfere, would kind of clash with the ribs of that individual. So therefore, they proposed, because of this, that they have that more semi-erect gait that I discussed earlier. Now, in Pachyrhinosaurus and in other centrosaurian ceratopsians, they don't have a very large medial tubercle. It's actually quite small in comparison. So this means that Pachyrhinosaurus wouldn't actually have this constraint. They wouldn't have the humerus interfering with the ribs if they were to stand more erect. So this means that Pachyrhinosaurus might have actually had a slightly more erect gait than Chasmosaurus. This brought me to look at more features in the forelimb to see if that was the case overall. So the next main element to focus on is the ulna, so this element here on the forelimb. And in both Pachyrhinosaurus and in Chasmosaurus, they have a very large olecranon process, this kind of large process on the top of the ulna here. And Thompson and Holmes noted that this large olecranon process would be very important for muscle attachments that would essentially keep the humerus from collapsing in on itself, given that semi-erect gait. Now, if an animal were to have a more erect gait, they might not need this large muscle attachment for that muscle, as they wouldn't have that same stress being placed on the humerus. So since Pachyrhinosaurus also has this very large olecranon process, it is more likely that they had this semi-erect gait. And lastly, another feature from the ulna is just a different view of that same element. In both Pachyrhinosaurus and in Chasmosaurus, they have a very large, what we call an anterolateral process. So just another process of the ulna. And in this step cycle, this is what forces the radius to move slightly more inward and forces the hand into what we call a more pronated position. So this process makes that whole mechanism of putting more stress on the manus possible. So therefore, these are all kind of reasons why I assume that Pachyrhinosaurus has that same step cycle and gait as Chasmosaurus. Furthermore, In Pachyrhinosaurus, I was also able to identify a very similar deformation to manual elements, to elements from the hand, as we saw in the Chasmosaurus specimens. The first one comes from a first metacarpal, so that's from the thumb, and the other one from the kind of pinky digit. And in both cases, they had a lot of deformation on the medial, on the interior side of the element, which led me to think that this might also be due to that added force from the step cycle. So if you compare the Pachyrhinosaurus elements to the Chasmosaurus elements, you start to notice that they do have actually pretty similar deformations. Although the Pachyrhinosaurus manual elements aren't quite as deformed, this might just mean that they didn't get to that same state as the Chasmosaurus, and they might have still been experiencing the same kind of deformation. Furthermore, Pachyrhinosaurus also has these very distinct kind of prominences, essentially just around a little bulbous structure on the metacarpal. And this seemed to occur on both sides. So I took this metacarpal and I performed a CT analysis, which is like a CAT scan if you've ever been to the hospital for one. But on a much smaller scale. So micro CT analysis kind of showed this very clear porous texture in the metacarpals, which seemed to actually coincide with those prominences on the different elements, or on the different sides of the elements. So whatever is causing this porosity is also causing this kind of swelling of the bone. So overall, based on all my findings, it seems likely that Pachyrhinosaurus would have had that same step cycle as Chasmosaurus. They have that same deformation in the manus. They have that same likely step cycle based on the different features I found in the forelimb. But as I mentioned before, just like with Chasmosaurus, this deformation probably isn't just due to that added stress from the step cycle. And there's probably more to it, if that's some sort of disease or infection. Now, previous authors made a few diagnoses of their own. And the first one was they presumed that this could have been something called dyschondroplasia, which is a developmental defect that causes the cartilage to degenerate and kind of erode away. And this is also known to occur in modern chickens today. However, since this is a developmental disease, we would expect to see it throughout development. So we'd expect to see it in younger individuals. But as I mentioned before, Pipestone has quite a lot of younger specimens from there, and there was absolutely no evidence of this pathology, of this deformation in any of the younger specimens. So that's probably not the case here. Next, they proposed that this could be a case of what we call hallux valgus, which is the deformation of the thumb. And you can see in both specimens here, the thumb isn't quite in line with the rest of the digits and instead kind of deviates inwards. This is typically concentrated to the first digit, but has also been observed in the fifth digit, which could also explain the element from the fifth digit that I found in Pachyrhinosaurus. And if we look at that first metacarpal, there is some level of what we call torsion, so twisting of the element, that could indicate that there is some sort of deviation of the thumb happening. However, since everything at Pipestone is what we call disarticulated, it's all apart, no bones actually are fit together as we find them. So there's no way to really know this for sure if this is a case of hallux valgus or not. Now, I presume that this may be a case of something called metabolic bone disease, or MDB. Now, this is a disease that occurs in the bones that causes overall degeneration and kind of weakening of the bones and leads to diseases such as osteoporosis. And this is actually the leading cause of nutritional deformations extant in living lizards, both in captivity, so both people's pets, as well as in the wild. It's also been found in living caimans and is closely tied to the animal's nutrition. Now, Pachyrhinosaurus is a very northern dinosaur. And as I mentioned before, that means that it probably experienced harsher conditions and more seasonal coldness than other ceratopsians. So it is likely that it actually had a reduction in its essential nutrients more often than other dinosaurs, which could have actually led to MDB occurring in this specimen. And this also could line up with my findings from the micro-CT analysis. Now, as I mentioned, MDB is known to cause diseases such as osteoporosis. And this porosity we are seeing in these elements very well could be that. However, based on previous studies, a key indicator of osteoporosis is the loss of what we call trabecular bone. So it's just a different type of bone that we might see in these CT analyses. But unfortunately, there wasn't really any evidence of any of that type of bone in these specimens or in these scans. So we don't know for sure on that front. Based on where these pathologies are actually coming from, so we're finding them in manual joints, this could be presumed to be a case of osteoarthritis. However, osteoarthritis is not known to cause this type of porosity. So even if that is the case, that doesn't explain what we are seeing in the CT analysis. Now, this type of porosity has been seen in other dinosaurs. For instance, Edmontosaurus metacarpal did have the same type of porosity identified in it. However, that was very closely, that was definitely tied to a callus that had formed around a fracture in the element. And in this instance, there is absolutely no evidence of a fracture in this metacarpal. So it's unlikely that that is the case here. All right, so that's all I have for you today. I hope you enjoyed it. Just kind of key take-home messages from my main findings were that we know that Pachyrhinosaurus lakustai lived to be at least 21 years old. Based on the latitudinal gradient hypothesis, though, it might actually be even older than that, as that might actually be an underestimation if flags were not actually deposited every single year. And furthermore, they seem to definitely share the same gait as Chasmosaurus and potentially had some sort of arthritic disease in their metacarpals and their digits. So thank you guys so much for joining us today and for listening to my talk. I really appreciate it. Now, we'll have a question period now, but if you do have any questions in the future, feel free to email me. I'm happy to answer anyone's questions. You can also follow me on Twitter at Becca Weiss, as well as Corwin Sullivan's lab at the University of Alberta. We do lots of really cool research there, not just done by me. So you can follow us at Ancient Anatomy. And yeah, so thank you very much for joining me today. And I guess it's question time now.
Awesome. Thank you so much, Rebekah. I can speak for the other employees at the museum that we always love to hear about Pachyrhinosaurus. So our first question here, Derek would like to know, when you looked at the growth, did you see any indication of sexual size dimorphism?
So I didn't see any evidence of that. That's a good question, though. I know that there have been studies before that have pointed out potential sexual dimorphism. That more so comes from the skull. It's really hard to determine that in the postcranial elements, as there's not too much variation between individuals. So it's really hard to determine if that is just a case of if it is a case of sexual dimorphism, or if that's just due to it being a larger individual.
Our next question here, has there been any research on the gait of non-ceratopsid ceratopsians? And how do you think the gait changed from the early to late members of ceratopsia?
That's an excellent question. Yeah, so actually earlier, so what we call basal ceratopsians, so things like Psittacosaurus, They occurred like much earlier than Pachyrhinosaurus or the very large ceratopsians. And Psittacosaurus in particular is actually really interesting because it is known to have, when it was a juvenile, it actually walked on all four legs, where as it grew up, it actually became a bipedal animal. So that means it walked on its back two legs. I'm not very sure on the gait in the terms that I was talking about today. But overall, I think any earlier ceratopsians still are thought to have that semi-erect gait.
Thank you. Lacerda would like to know if it is possible that the pathological manus is caused by the same semi-erect gait for an extensive time. Something along the line of bad posture in humans can cause skeletal diseases.
Yeah, no, that is definitely possible. It's kind of hard to determine that for sure, and that's why I made sure to actually scan the specimen, because that gives us kind of more information. If it is just due to something along the lines of bad posture, then we want to rule out all of the possibilities for disease. So there's certain features, as I mentioned before, that we can look for to determine if it is a specific disease. But if we don't see any of those features, then it's probably more likely that it is just due to that repeated stress.
Fantastic. Cam would like to know, what is your favorite Saurischian dinosaur? Ornithischian, I'm not pronouncing that right, dinosaur.
Ornithischian, yeah.
And prehistoric invertebrate.
Okay. So for those of you who don't know, Saurischian dinosaurs refer to sauropods and theropods, so the long-necked dinosaurs and the kind of carnivores. I don't really think about those dinosaurs much. I'm so focused on ornithischians. I think I'm gonna be pretty basic here and say T-Rex. Maybe Albertosaurus. Albertosaurus is pretty cool too. But I like the big meat-eating dinosaurs. I think they're really cool. They're like, it's what you get from watching Jurassic Park too much as a kid, I guess. And following that, my favorite ornithischian dinosaur, so again, just a bit of an explanation, ornithischians refer to like ceratopsians, hadrosaurs, that's like duckbills, things like stegosaurus, kind of all of the rest. Yeah, I'm going to be very biased there and say Pachyrhinosaurus because I have studied it in detail and I think they are pretty cool. And sorry, what was the third one?
And your prehistoric invertebrate.
All right, so invertebrates, so that's like insects and bugs. I think trilobites are pretty cool. I don't know too many really interesting ones, unfortunately.
All right, next question. Was there anything you found in your thesis with this species you'd like to keep researching? Next steps to continue this research, and she says, amazing talk.
Oh, thank you. Thank you very much. Thank you for listening. So actually, kind of a big thing to continue my research would be interesting, because so my thesis all focused on the forelimb and shoulder girdle of Pachyrhinosaurus, and I found quite a few interesting things just by studying that. So it would actually be really interesting to study the rest of the postcrania. So like I said, in ceratopsians, everybody focuses on the skulls. The skulls are really cool. They're very interesting. They have a lot of very cool features. But there's definitely a lot that we can gain by studying the postcrania, and that hasn't actually been done all that much. So it's kind of a change in ceratopsian paleontology to try to focus on that. In most other species or groups of dinosaurs, there have also been kind of key features, really cool findings that have come from studying the postcrania. So I think there's definitely more to learn by studying the rest, so studying the hind limbs, the pelvic girdle, things like that.
All right, next question. What's the scale of research at the Philip J. Currie Dinosaur Museum?
Sorry, what is the scale of research?
Yes.
I'm not sure. I am actually the best one to answer that. Although I've done like my research at the Currie Museum, I know that those that actually are at the museum are still trying to do their own research. Every year we my lab from the University of Alberta kind of goes out and we join up with members from the Philip J. Currie Museum to do our fieldwork. So the big thing is that we are trying to expand the knowledge of Grand Prairie paleontology. It's one of the locations that we don't actually know that much about. Only recently are we really actually getting an appreciation for what types of prehistoric animals live there. There's quite a few quarries that we work on most years that we find so many elements from so many different types of prehistoric animals that it gives us an idea of what the ecosystem looked like as a whole. So I know this isn't specifically the Philip J. Currie Museum, but just Grand Prairie paleontology is really kind of taking a lead in the paleontological game as we're trying to learn as much about Grand Prairie as we do about other places like Dinosaur Provincial Park, for instance.
Great answer, thank you. Koi would like to know, can CT scan differentiate trabecular bone from cortical bone? If not, I figure we can always make thin sections to see whether those pathological metacarpals actually suffer from any loss of trabecular bone.
Yes, I completely agree. So the CT scans that I did didn't come out at as great of resolution as I would have liked. And otherwise, we could actually be able to identify the difference between those two types of bone. Thin sectioning these metacarpals definitely would be the best way to answer that question. However, the main problem with thin sectioning elements, so like I said, when I was sectioning the different humeri, you don't want to cut up specimens that are like prize specimens. So especially with these metacarpals, we only know of these two different metacarpals from Pipestone that actually have this deformation. So we don't really want to perform what we call destructive sampling. We don't actually want to cut up these specimens unless we have something else to fall back on.
Okay. Robin would like to know, what's the most interesting fossil you've ever worked with?
Most interesting fossil? That's an excellent question. Okay, this isn't really one that I have worked on specifically, but it's actually one that is in the, or at least last I checked, was in the lab at the Philip J. Currie Museum. And it is this plesiosaur specimen, so like a marine reptile that actually has these stones in the stomach. So would have you actually use these to kind of grind up its food? So I always find specimens like that so interesting when we can actually see what the contents inside these animals is. Yeah, I guess so.
I couldn't agree more. Yes, that one specimen is still at the museum. It's one of my favorite to show off. Sam would like to know, what do you hope for the future of paleontology in Pipestone Creek?
So I hope that research continues there. So like I said, the Currie Museum is still doing annual fieldwork at the site. And I really hope that that continues because we actually have taken, or I haven't personally, but there have been core samples taken from that site from farther back into the hill. So we actually know that this bone bed expands approximately the size of a football field. And we've only excavated a fraction of it. There's still so much that we can find there. If we keep excavating it, I'm sure the more we look, the more interesting finds we have. You never know when you'll find the next really cool deformed element.
Awesome. Well, I think that concludes our question period. Thank you so much for being here with us. And congratulations on finishing your master's recently.
Thank you very much.
Great. That concludes our summertime speaker series. I want to send out a big thank you again to Dr. Bamforth, Dr. Zazula, and Dr. O'Connor. If you missed any of these speakers, you can find their presentations on our YouTube channel. And stay tuned to social media pages for announcements of our fall series. All right. Bye, Rebecca. Thank you. And thank you, everybody, for joining in.